Hello, this is Rick Powers from Western Technical College, making a video for basic statistics. Lesson number 12, Probability Rules, Part 1. Hello, this is Rick Powers from Western Technical College, Basic Statistics. Lesson number 12, Probability Rules, Part 1. Now we want to consider situations in which we would need to add, subtract, multiply, or divide probabilities. First, we consider adding and subtracting. In order to understand the process, we have a couple of definitions to consider. The first idea is sets which are mutually exclusive or disjoint. Sets with this relationship have no items in common. For instance, you can't be under 18 and over 40 at the same time. Those are disjoint sets. But you can be under 18 and play basketball at the same time. Those are not disjoint. The next definition is the special use of the word or in set theory. When I consider set A or set B, I am including all the elements of A as well as all the elements of B. Example, people under 18 or 19 to 25 would be everyone up to 25 years old. Since we include the elements, it makes sense to add the number of elements together. And if the sets are disjoint, then that will be all that's needed. So then for disjoint sets, probability of A or B equals the probability of A plus the probability of B. Example, I create a game of rolling one die and I win if I get an even number or a 5. What is my probability of winning? Since these are disjoint sets, probability of A or B equals probability of A plus probability of B. Therefore, the probability of getting an even number plus the probability of getting a 5 equals 3 out of 6 plus 1 out of 6, which is 4 out of 6, or 2/3. Well, then what if the sets are not disjoint? Consider this example. If we add the number of students in the classroom who wear jeans plus the number who wear a hat, we need to consider the overlap of the categories. That is, anyone wearing jeans and a hat at the same time. We don't want to count them twice. The statistical description of those people who are in both categories at once is the word and. Another descriptive word is intersection. So back to the question, how do we account for the overlap of categories if we want to include everyone without double counting? We will count everyone in both groups and then subtract the double counted. This is the general addition formula. Probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. It works for all sets, whether disjoint or not. Example, I want to do a survey about fashion and I want to include those who wear jeans and also those who wear hats. In the classroom of 20 students, there are 10 people wearing jeans, there are 6 people wearing hats, but those numbers include 2 jeans and hat people. So then what is the probability of choosing a person that I want? Probability of A or B equals probability of A plus probability of B minus probability of A and B. In this situation, the probability of jeans plus the probability of hats minus the probability of jeans and hats. 10 out of 20 plus 6 out of 20 minus 2 out of 20 equals 14 out of 20, which is 70%. There is another situation that often comes up in statistics where we ask the question, what if the event does not happen? Most people understand that if there's a 20% chance of rain, then there's an 80% chance of not rain. These are disjoint sets of outcomes because it has to be one or the other. Since these are disjoint sets and they include every outcome, the probability of A plus the probability of not A must be equal to 1. So then, the probability of not A equals 1 minus the probability of A. This is called the complement rule, since the two possibilities include the complete set. The next topics, multiplying and dividing probability, are very important ideas in statistics. We will start with an introduction, then the next lesson will continue the topic. Consider what happens to the number of outcomes when you are choosing twice. For example, I'm getting a cookie and a drink. How many outcomes are there? Well, there are 5 types of cookie and 15 kinds of drink. So for each type of cookie, I still have 15 drink options, so I multiply. That means I have 75 different outcomes. Consider then getting a sandwich, a snack, and a drink at the cafeteria. Maybe there are 18 different sandwiches, 15 different snacks, 20 different drinks. That gives us a lot of options. 18 times 15 times 20, 5,400 outcomes. I've had members of my family who have struggled with mental illness and anxiety. Just think about someone who is convinced they are supposed to pick the absolute best combination of all of those options. In our affluent culture, all the choices can be overwhelming. So in finding the number of outcomes, every time we make a choice, we multiply by the number of options for each choice. Example, rolling 2 dice will create 6 options for each die, so 36 total options. Note, the order is important. 3 and then 4 is not the same as 4, 3. This creates a situation where we will want to multiply the probabilities. For example, I create a new game where I have a red and a blue die. I'll win by getting an even number on the red one and not a 1 on the blue one. What's my probability of winning? Let's consider counting the outcomes first. There are 3 ways to get an even number on the red one, and there are 5 winning outcomes on the blue die, so that's 15 outcomes. Probability is then 15 out of 36, which is 5 over 12. But we could also multiply the probabilities. 1/2 times 5 over 6 equals 5 over 12. A tree diagram is one method to organize the outcomes. Here's what that last problem would look like. Getting an even number on the first die, 2, 4, 6. Getting a number that's not equal to 1 on the next die, 2, 3, 4, 5, 6. Note that we multiply 3 times 5, 15 outcomes out of the 36. There is a specific word used whenever we're able to multiply probabilities like this: independence. It means that doing one process does not affect the other. and tree diagrams assume that the processes are independent. Example, if I roll one die, it doesn't affect the roll of the other die. In the next section, we will discuss situations where events are dependent, where one event changes the probability of another. Example, the number of days of snowy weather affects the number of accidents. But for now, simple multiplication will work for situations with multiple events. End of lesson 12.